well, what is the next step? The next step in optimization is when you're dealing with two functions instead of one function. What do I mean by that? Optimization. Now we are dealing with Lagrange multiplier method. So this is a method that was developed to help mathematicians finding the maximum or minimum value of a function which is constrained to another function. Well, what do I mean by that? Lagrange multiplier. Okay. Let me find a cool thing. So, suppose you are a manufacturing company and your job is to produce this piece, stationary piece. So you have a company and you want to produce this with this dimension, and then you have some purchasing obligations. Of course, it's material. You need to use the material wisely. Okay, well, and this is the exact shape, the exact product, the exact option that you have for producing. You cannot change anything here. Well, okay. At the same time, another company is producing this piece for you. So you have this piece and another company is producing this piece for you. Well, you are wondering, you want to know how to maximize the volume of this option here, of this object here that can fit this object. It needs to fit. Let's see. So again, you're trying to maximize this object. Another company is producing this piece for you, and you want to make sure this maximized volume can fit this object here. How do you do that? Okay, this is your function f, and this is another function g. Well, these are objects. These are 3D objects in the space. This is one surface. This is another surface that you have. Well, you're trying to maximize this volume that fits this object. One method is using Lagrange multipliers. How does it work? So in this method, the goal is to maximize or minimize function f of x and y. So you have the option to change this function. Well, you have a constraint, function g. but we have a constraint. Function g of x and y, which is equal to a fixed value. As you remember, there is another company that is just producing these, and it's fixed in dimension, in materials. You don't have any freedom to ask them to change these. You cannot ask them to, okay, make it larger, make it smaller, make it bigger. You don't have that option, and you don't have that freedom. The only freedom that you have is on your own product. Okay. So what are we going to do? It happens that this function can get its maximum or minimum value, or in general, its optimal value if and only if the gradient vector of f is parallel to the gradient vector of g. So it turned out f of x and y can get its optimal value if and only if the gradient of f, which is denoted by gradient of f, is parallel and in the same direction of the gradient of function g, gradient of g. So to solve this problem, we're going to set it up this way. So we set these as gradient of f equals to lambda gradient of g, and this lambda is called Lagrange multipliers. This lambda is called the Lagrange multipliers. By solving for lambda and finding possible x and y values, we can find the optimal value for function f. The rest is solving for lambda, x, y, find all possible values by using different methods in algebra. So the rest is just algebra. By using algebra. It has nothing to do with calculus. After this step, whatever we're doing is algebra. We're trying our best to apply whatever we learned in algebra, multiplying, dividing, substituting, adding to find the possible values for lambda, x, and y. Substitution or addition or multiplication or any other method that we learned in algebra. Division to find possible values, proper values, acceptable values for lambda, x, and y. Well, as you can see, here you have, for example, two functions. One of them is function f, and the other one is a fixed function g that you cannot change its dimension. This is your function. Well, it happens that the level curves of function f and the level curves of function g, they're going to be intersecting at some points. That makes sense. But the optimal value for function f happens when gradient of function f and gradient of function g are in the same direction and parallel to each other. There you go. Give us an example. Okay, example. So this example says, find extreme values. Find extreme values, maximum, minimum. A function of f of x and y equals to x squared plus 2y squared, 2y squared on the circle, x squared plus y squared equals to 1. There you go. So here we have a function. Well, this function, as you remember that the graph is actually you're going to have a minimum for this function if you take a look at the graph, and this is a circle. It means that we're trying to cut this function using this fixed function, this circle, and find the optimum value for this function. What is it maximum and what is the minimum value for the function over this circle? Okay. And so since we have two functions, one of them is f of x and y equals to x squared plus 2y squared, and the other one is a fixed function, g of x and y equals to x squared plus y squared minus 1. We cannot change this function. This function is a fixed function. We can apply Lagrange multipliers. Well, so far it's not that bad. We know that to apply the method of Lagrange multiplier, we need to find the gradient of f and also the gradient of g, set them equal to each other, because at the optimal value for f, the gradient of f and the gradient of g are parallel to each other. So let us find the gradient of f and the gradient of g and set up gradient of f equals to lambda gradient of g. It means that we need to find the values that these two vectors, these are vectors, are parallel to each other. So the gradient of f is equal to, we have a vector 2x, this is f of x, comma, f of y, which is equal to 2x, comma, 4y. Well, the gradient of g is equal to g of x, comma, g of y, which is equal to, well, it's not that hard, 2x, comma, 2y. Gradient of f must be equal to lambda gradient of g. What's the meaning of that? It means that 2x comma 4y is equal to lambda 2x comma 2y. The rest is algebra. Now use algebra. Okay, there you go. So here you have 2x comma 4y equals to 2 lambda x comma 2 lambda y. So the first components must be equal to each other. The second components must be equal to each other. It means that we have these two equations. 2x equals to 2 lambda x and 4y is equal to 2 lambda y. Okay, let's write them down here. We can analyze them with more space. 2x, 2 lambda x, and 4y, 2 lambda y. So from the first equation, if lambda is equal to 1, 2x is equal to 2x. So let's call this 1. Let's call this 2. From 1, lambda is equal to 1. From 1, you get also x equal to 0. Also, x equal to 0 is acceptable. Why is that? 0 times 2 is 0. 0 times 2, lambda is just a number. It's a multiplier number. 0 times 2 lambda is also 0. 0 and 0 is equal to 0. Since 0 is equal to 0. What about the second one? So if lambda is equal to 1 in the first equation, lambda cannot be 1 in the second equation. Why is that? We get 4y equals to 2y, and the only option that we have is lambda of 1y equal to 0. So from 2, y is equal to 0 is acceptable since 0 is equal to 0. Okay. Do we have any other piece of information to use? Take a look at your example. Take a look at definitions of these two functions. Remember that this guy, it can take on different values, and it gives you a z value which is related to that x and y. But from this circle equation, if you plug in something for x, you can evaluate y. If you plug in something for y, you can evaluate your x. So let's erase this one, and now from x squared plus y squared. X squared plus y squared equals to 1. If x is equal to 0, I get y squared equals to 1, or y is plus minus 1. If I plug in y equal to 0 into x squared plus y squared equals to 1, then y squared is 0, so we get x squared equals to 1, x is plus minus 1. So how many points do we get? X is 0, y is plus minus 1, y is 0, x is plus minus 1. So the possible points, 0, 1, 0, negative 1, 1 and 0, negative 1, and 0. We found all critical values that help us to find the optimal value for if I plug in 0 and 1 into the function, my z is 0 and 1, my z is 2. If I plug in 0 and negative 1, my z is still 2. If I plug in 1 and 0, my z is 1. So it takes on its maximal value, which is 2. It takes on its minimal value, which is 1. There you go. Let's take a look at another example. Find extreme values of function f three x plus 5 plus 5, and it's constrained to x squared plus y squared x squared plus y squared equals to 10. There you go. So since you have two functions, let us apply Lagrange multiplier. We have two functions. So the first one is f of x and y, which is 3x plus 5. And the second one, g of x and y, your constraint, which is x squared plus y squared minus 10. To apply the Lagrange multipliers, find the gradient of f, find the gradient of g. What are these two? So the gradient of f, which is equal to the vector function f of x and f of y, equals to the gradient of f is 3, 1, just a fixed vector, and the gradient of g is equal to, well, you're going to have a vector function 2x, g of x and g of y, 2x, and 2y. Now, we know that the optimum value for f happens when the gradient of f is parallel to gradient of g. Now, set the gradient of f equals to lambda gradient of g. 3 and 1 is equal to lambda 2x, comma 2y. The rest is algebra. Algebra says 3 and 1 is equal to 2 lambda x, 2 lambda y. The first components must be equal to each other. These are just simple vectors. The second components must be equal to each other. Well, what do we have here? It says, okay, 3 is equal to 2 lambda x, and 1 is equal to 2 lambda y. So, there you go. How we can analyze this? Which method is most helpful here? Should I just plug in random values for lambda? Should I isolate lambda on one side and substitute that? Should I divide these two? Should I multiply these two? Which method? Well, one thing that comes to mind is, okay, I have two equations. Somehow I want to get rid of lambda. And also note that you have another equation to keep your eyes on. This is another important relation between x and y that can help you to find the values for x and y. So from these two equations, what you can do, you can either isolate lambda on one side, substitute that in the second equation, or you can divide these two equations. Both of them work. So we can isolate lambda on one side, then substitute in the second equation, or just divide these equations. Okay, if you isolate lambda on one side, you get lambda equals to 3 divided by 2x. So let's call it 1 and 2. From 1, lambda is 3 over 2x, and substitute in 2. From 2, you get 1 equals to 2 times 3 divided by 2x times y. You're finding a relation between x and y. So x is equal to 3y. I found the relation between x and y. I also have another relation between x and y. Also, x squared plus y squared is equal to 10. So just substitute this guy here. X is 3y, substitute that in this equation, solve for y. So you get 3y squared plus y squared equals to 10. So you have 9y squared plus y squared is 10, or 10y squared is 10. So y is plus minus 1. Y is plus minus 1. So what is your x? X is, if y is 1, then your x is 3. If y is negative 1, then your x is negative 3. So what are those points? 3, 1, negative 3, negative 1. Are the